Welcome back, everyone. Next, we have ASP Isotopes Inc. It trades on the NASDAQ under the symbol ASPI and is a pre-commercial stage advanced materials company dedicated to the development of technology and processes to produce isotopes for use in multiple industries. Please welcome its CEO, Paul Mann. Nice to see you today, Paul.
Thanks again for having me back. It's great to be back. Thank you.
All right, the floor is yours.
Thank you. So we'll go through the first slide deck and prepared remarks for the first sort of 15, 20 minutes, and then we can go to Q&A. So we'll run through the slide deck now. So obviously we're a public company, so we have a forward-looking disclaimer and statements. Please look at our 10K for risk factors and what have you. So what are isotopes, or what do we do, and what's our company? So ASPI says we make very special chemicals. We describe exactly what isotopes are in a moment, but isotopes are used. You touch isotopes every day, you don't really know it. They're used in medical, used in semiconductors, and obviously nuclear energy. And our company has three verticals within it. ASP Isotopes is where we founded the company 3 years ago, and that produces stable isotopes that we sell to customers. We can sell to customers around the world. Our goal is for that business to be cash flow positive as we exit this year. On the left, you see PET Labs. So PET Labs is a radio pharmacy. These produces short-lived or short half-life isotopes, and they're used in the treatment of oncology and cancer. And actually, PET Labs is the leading supplier of fluorinated PET isotopes in sub-Saharan Africa. We have a big business down here, and it's going really well. And that business is cash flow positive already, and we hope to grow it over the next several years. We're actually going to try and triple the size of the footprint in South Africa over the next couple of years. And then Quantum Leap Energy is our nuclear fuels business. We incorporated about 12 months ago, and that will focus on the nuclear fuels of the future, specifically high-assay, low-enriched uranium, and lithium-6 and lithium-7. And we'll talk more about what those fuels do later on in this presentation. So here are milestones for 2024. You can read those quickly. Our goal is to sign more supply agreements, to get certainly ASP Isotopes to carry positive annual operating cash flow, and then supply additional supply contracts to build plants elsewhere in the world and to turn this into a kind of more of a global business. So what are isotopes, you're all asking? So when you think about different chemicals, so oxygen, carbon, hydrogen, they all have different positions on the periodic table. Different numbers of protons in the nucleus determines their chemical properties. And you can separate all of those elements via chemical processes. They're very, very different. Hydrogen, carbon, and oxygen are all very different chemically. But when you take something like an element, often the same element has different isotopes, where they have different numbers of neutrons in the nucleus. And that means they have the same chemical properties, but often have different physical properties. So let's take silicon as an example, silicon that's used in semiconductors. You also find silicon on the beach. It's basically sand. If you take a kilo of silicon, it has 3 isotopes in it: silicon 28, 29, and 30. And they each have different masses: 28, 29, and 30. 28 and 30 are really good at conducting, but 29 doesn't conduct. And actually, if you can remove the 29 isotope from silicon, then you can make silicon that conducts thousands of fold faster and also conducts heat better as well. So, what does that mean for semiconductor companies? Well, maybe they can make faster semiconductors, and semiconductors that enable quantum computing. So, what does that mean for price and what we do? Well, you take a bag, a kilo of sand, normal kilo of sand you buy in the shop, it's probably about $1 a kilo. When you enrich it in the 28 isotope, it's more like $600,000 a kilo. When you look at something like carbon, so take a bag of charcoal, probably $1 a kilo as well. A kilo of carbon-14 is about $24 million a kilo. So we take these really basic elements or chemicals and convert them to very special materials that have special applications that the world requires and needs. So one of the reasons I got interested in this industry 3 or 4 years ago was because I've recognized this for a number of years, and the supply chain is particularly challenged in isotopes. There are only really 2 producers today in the world, There's no domestic US isotope production using kind of methods that we use. And, basically Russia supplies 85% of the world's isotopes. So how do we separate isotopes? Well, we have two technologies that we use. The first is the aerodynamic separation process, and the second is the quantum enrichment process. And both were developed during the kind of the nuclear era in South Africa, during the kind of the 80s and early 90s. Now, the ASP process is similar to a standard Russian centrifuge, in that a centrifuge you'd put it vertically on its vertical axis, and you'd spin it around very quickly, and the heavier isotopes move to the outer side. The lighter isotopes don't move quite as much, and you can separate heavy from light at that wall. They cost billions to build. They're huge. They take forever to build. Urenco says it's going to build another centrifuge in the United Kingdom. They're starting now. Hopefully, it's ready by 2031. Our process is much more simple. We have a vertical tube. We keep that tube stationary, and we spin the gas inside the tube. And what that enables us to separate heavy from light. We put it through various flow directors where the gas bends around certain corners, and that allows us to get some enrichment. Now, the advantages of our process is that it's substantially cheaper. Our plants cost maybe tens of millions of dollars to build. They're much smaller. They're modular. And also, we can enrich light isotopes, where masses are very light, things like carbon-14, silicon-28. They're really challenging to enrich in a large centrifuge. They need heavy masses. The downside of our technology is that we use slightly more energy to do our enrichment, and that's one of the reasons why we are looking to move to Iceland later this year to build plants there where energy is extremely cheap. The second process, quantum enrichment, doesn't really use much energy. Basically, this is very good for stuff you can't convert into a gas very easily. And we put the metal in the bottom of a vessel, and we heat the metal up and we vaporize it. We pass the vapor through a laser. The laser hits the stream, and it ionizes or excites one of the isotopes. We can collect that on a charge collector plate, and that allows us to separate one isotope from the mix. So this just summarizes our technologies neatly. So nuclear medicine is a very large opportunity we're looking to move into. This just gives you some stats about the medical isotope market. It's huge. It's growing very fast. Lots of new drugs coming to market right now. And this chart here kind of shows the symbiotic relationship between ASP Isotopes and PET Labs. So ASP Isotopes produces stable isotopes. So these are things you can ship in a FedEx package. They don't decay. They're often naturally occurring, but obviously in mixtures. A radioisotope decays and gives energy and radioactivity as it decays, and we can use that energy and that radioactivity to treat various ailments and diseases. So PET Labs consumes a lot of stable isotopes. ASPI produces stable isotopes. So this is the largest opportunity we have, which is molybdenum 100, and the molybdenum 99 market today is over $4 billion. And molybdenum 99 is a radioisotope produced in various nuclear reactors around the world, and it decays to produce technetium 99. Technetium 99 is the workhorse of nuclear medicine. The problem is that you've got this Moly 99, you're shipping it around the world, and it's halving in value every 2.5 days. We believe that molybdenum 100 is a better way to produce technetium 99. You can convert it to technetium 99 almost at the point of care. You can ship molybdenum 100 in a normal FedEx package. You can store it on the shelf. So this, we think, is a huge upgrade to traditional ways of producing radioisotopes. Be warned, though, this is not going to become a large revenue driver for us anytime soon. This is it's a slow market to get into. Healthcare markets move more at the rate of a glacier rather than a river. But we're ready to supply this market when they're ready for us, and hopefully in the next several years we will start to gain some customers. This next market will move a lot more like a river rather than a glacier. So this is a ytterbium-176. So Novartis's new oncology drug called Pluvicto requires a radioisotope called lutetium-177. That's produced by ytterbium-176, and today the only supplier of ytterbium-176 to the market in commercial quantities is Russia. We hope to have our first plant up and running in kind of September, October this year. with first production, just a few grams coming in the December timeframe, and hopefully significant number of grams coming during 2025. We're in discussions with a lot of customers about their needs and requirements here. And hopefully we'll be able to announce some customer contracts in the next sort of weeks or months. And Zinc 68 is likely going to be our first plant in Iceland. Zinc 68 is used to make gallium 68, and that's used as a diagnostic marker for anyone who's going to use one of these new lutetium actinium-based drugs. You have to diagnose the patient first using a gallium 68 scan. And so, we're looking to sign our first couple of contracts here in the next, call it, couple of months, and then that'll allow us to build our first plant in Iceland. This is our first plant we ever built. This is a carbon-14 plant. It's based in Pretoria, South Africa, and we expect to start producing this in the next sort of few weeks with commercial production by the end of the year, or during the second half of the year. And we've signed a multi-year take-or-pay contract with a Canadian customer for a minimum of about $2.5 million a year. The total market size here is about 10. Maybe they want some more in the first 2 years. We'll have to see. But this is a very exciting product to be launching to the market. The market is desperate for this isotope right now. Russia, again, is the only producer of this isotope. And, we've got a lot of interest from customers who want to buy it from our partner who'll be selling this. This is a very high gross margin product, this one is as well for us. So here's just a timeline of when we expect or when we hope to launch each of these isotopes and when they hope to come to market. So semiconductors. So as I mentioned earlier, silicon-28, when you remove the 29 isotope, becomes a lot more conductive. Now, we initially thought this was a market really for quantum computing. Who knows when quantum computing is going to really crystallize? Maybe it's a couple of years, maybe it's 10 years. But more recently, semiconductor companies have got very excited and aggressive about trying to acquire some silicon-28 today, maybe to try and put into more advanced semiconductors. And the properties of silicon-28 will mean that, per scientific literature, you'll be able to make semiconductors that are much more effective, much more faster, can process things a lot more quickly, and also conduct heat better and have less buildup of heat. And one of the big problems you're finding in data centers is the amount of heat that gets built up and how much cooling that needs to take place. We're also looking to use gallium 7072 as well. So it's a germanium 7072 as well, and that will hopefully be coming from the same plant later this year. And we've signed 2 contracts for silicon-28, and we're looking to sign about 3 more in the coming months. As I mentioned earlier, South Africa does not benefit from a low-cost energy standpoint, so we're looking to start building plants to go into Iceland. We've signed a long-term energy supply agreement. We've found some real estate. I think we've got 3 of our 4 permits already achieved, and we've got 1 permit to go. And we're looking to sign the first contract for Iceland fairly soon. So let's move on to nuclear energy now and quantum leap energy. So, the problem is fairly well known. The world has to double or more the amount of electricity and energy the world produces over the next sort of 25 years or so. You have to do that whilst maintaining carbon neutrality. Now, obviously, solar and wind are great if you have sun, if you have wind. But if you don't have sun and you don't have wind, it's a real problem. And most governments, I think, believe that the only real solution to have a low carbon base load energy to the grid is nuclear. And so many countries have said they're going to triple the amount of nuclear capacity by 2050. And you'll see on this page here some of the examples of countries that are working to do that. Now, we believe the future of nuclear energy is the SMR, the small modular reactor. I think that's probably becoming a consensus view. And some of the companies involved in this industry are things like TerraPower. That's the chairman of that's Bill Gates. Oklo, the chairman of Oklo is Sam Altman. X Energy, Rolls-Royce. And, the way a small modular reactor works is that it's a small reactor that you can place in any city, and think of it like a 40 to 60-year battery. What made cars really cheap was production line manufacturing, the Ford Model T. This is taking production line manufacturing to the nuclear industry. And suddenly, the costs of building these reactors drops dramatically. Also, reactors of yesterday were huge installations, 1, 2, 3 gigawatts, built in the middle of nowhere. It takes forever to get the transmission lines into the city where people are going to use it. These are much smaller. You can put them right in the outskirts of the city or next to a manufacturing hub. And as I said earlier, it's like a 40 to 60 year battery with really cheap energy. The problem is all these reactors require a new type of uranium called HALEU, high assay low enriched uranium. And when you think about traditional uranium used in a standard low pressure water reactor, that's enriched to kind of 3.5 to 5%. This is enriched to 19.75%. And today there is no Western producer of HALEU in commercial quantities. We've signed 2 MOUs with large SMR companies who collectively require over $37 billion of HALEU between now and 2037. And right now they have no producer of that fuel. So I've described our technology to you already. We vaporize a metal, pass it through a laser beam, and we can collect the ions. This chart here kind of compares various methods of enriching isotopes. And you'll see second from the left is a centrifuge. And, the selectivity here, the alpha is the line to look at. That tells you how much efficacy or enrichment you get per stage of enrichment. And so here you see the selectivity, the alpha is 1.15. And so for a centrifuge, you basically cascade these in a long line, and you compound that 1.15 over the cascade, and you get the enrichment, the desired level of enrichment that you need. Our process is quantum enrichment, and that has a selectivity much greater than 50. So greater than 50 versus 1.15. We feel quantum enrichment can really change how people enrich isotopes. And we feel this is the next generation form of enrichment. Here's some quantum enrichment in real life experience. And so this is actually published data. This is published in our Chief Technology Officer's PhD. This is for the enrichment of lithium-6 and depletion of lithium-7. So the top chart there, you see the lithium-6, or the lithium feedstock, and the lithium-6 is at 7%, lithium-7 is at 93%. After a single pass through the enrichment chamber, you will see that the lithium-6 is now at over 90%, and the lithium-7 is below 10%. So that has a light side enrichment factor similar to an alpha of 112. So 112 versus 1.15. That gives you an idea of the order of magnitude of just how efficacious this process is. Now, why is this important? So this kind of shows how nuclear fuel prices have changed over the last sort of 10 years or so. And you'll see that the current squeeze on the supply side and the demand and geopolitical factors are really kind of pushing prices to 10-year all-time highs. And it's quite interesting to think of a commodity which has increased in price fivefold, and you haven't seen a supply side response. That I think is quite remarkable. Having been investing in commodity chemicals for many years, it's very rare you see that kind of price inelasticity. And when you think about HALEU with these new higher prices, HALEU today, if one could produce it, would be over $20,000. When most of these SMRs were kind of thought up and designed, people were expecting HALEU between $5,000 and $10,000. And that really does hurt the economics of a lot of these projects. Of that HALEU, about half of it is just the feedstock, the uranium ore that is dug out of the ground. About 1/6 is the conversion where you convert it into UF6 gas, and then about 1/3 is the actual enrichment, which is where we're focusing on. But what makes us excited is that our enrichment factors for quantum enrichment are so much higher than what you see with a centrifuge. We'd like to think that we can take depleted tails, so nuclear waste, and convert that straight into HALEU. And that would do a number of things. First of all, it would clear up an environmental problem that is growing. In that picture there, you see cylinders of UF6 waste sitting in Ohio. Each one of those cylinders has about 20 metric tons of uranium hexafluoride gas. And secondly, if we can eliminate our feedstock costs, it would really change our cost of enrichment. And that would allow us to get HALEU down to a really low price that could really change the outlook for nuclear power, particularly in emerging markets. And you have to price nuclear power at a discount to hydrocarbon-based energy if you're going to have any success in driving nuclear power into emerging markets. So this chart here just shows, where we're at in terms of chlorine-37, lithium-6, and uranium-235, which are the kind of the three nuclear fuels that we're working on. Just to summarize, we have a proven proprietary technology, two different ways of enriching isotopes. Both were developed in South Africa many years ago, been advanced over the last 20 years by our scientists. There are multiple secular and geopolitical tailwinds right now helping drive demand for the stuff we're producing. We have 3 plants starting up hopefully between now and the end of the year, and we look forward to building a lot more plants in the future. So I'll stop there. I'll take any questions. That's exactly 20 minutes, leaving you 10 for Q&A.
Great job, Paul. We do have some questions for you. So elaborate on what your future plans for the company are with regards to splitting out quantum leap energy and uranium enrichment from the medical's isotope divisions, please.
Yeah, so we've always said that a nuclear fuels business and a nuclear medicines business are very different businesses. We have similar technologies we can use in each, but the regulatory, the licensing, the customers completely different. So we've always said that we're going to spin out quantum leap energy at some point in the future, as soon as market conditions will allow. And we'll also historically said we're going to do an IPO at the same time to raise some additional capital into quantum leap energy. Now, having spoken to bankers and various discussions with them, we've realized that maybe an IPO was not the most appropriate way to raise the capital into quantum leap when we spin it out. So we raised about another $35 million last week. And we'll use a lot of that capital to go into QLE so that when we spin QLE out, it's fully capitalized already rather than requiring an IPO. So right now, today, if you own a share of ASPI, hopefully at some point in the near future, you'll own a share of ASPI and a share of Quantum Leap as well. And we look forward to doing that at some point, maybe later this year, next year, as soon as we can. I think we need to hit a couple of milestones before we do that spin out. I'd like to think we have a clear strategy on where we're going to build our first quantum enrichment facility for HALEU, and also potentially have our first lithium 6-7 plant in construction. So they're the two main milestones we have to achieve before we can do that separation.
Perfect. Thank you for that answer. Olivia asks, what's your relationship with PET Labs? Is there a contract with them? Are you exclusive supplier?
Yeah, so we own 51% of PET Labs, and we supply certain things to PET Labs as well, but it's not exclusive. And I would expect the amount of isotopes we supply to them over the next several years will increase as we bring online zinc-68, bring online ytterbium-176, that kind of stuff. And also, we're talking to a number of other businesses, a bit like PET Labs, who may want to come and kind of join the PET Labs franchise over the next several years. To be able to be vertically integrated to a supply of stable isotopes puts you at a huge competitive advantage over any other radiopharmacy. So we'll have to see how things go there. But we're very happy with how PET Labs is doing. It's growing its revenues well. And it's a great business. Sub-Saharan Africa's largest supplier of fluorinated radioisotopes.
Fantastic. Aaron says, Aaron read that insiders have been buying the stock. So this is a great confidence booster. Is the company doing any sort of buyback?
We're not doing a buyback right now. We haven't got approval for one, actually. And we're not generating free cash flow right now either. But, I would have thought as we start generating free cash flow and the CapEx cycle slows down, we'll look to return cash to shareholders in the most effective way, which is probably, a combination of dividends and buyback. That's my guess.
And
I'd actually add also on that previous point, management have participated in most rounds this company has done. So typically when we raise money with external investors, management normally participate as well. So myself, the chief operating officer, participated in the raise last week. We put in about $150,000. I think at the raise we did last October, the independent directors put in about sort of $300,000 then. The IPO, myself and another one was in for $150,000. And then the $2 round and the 25-cent round, we were probably in for a total of maybe a couple of $1 million. So, we have a good, if we ask investors for money, then we open our wallets at the same time.
Perfect. Brito wants an update on the Iceland plant and the status of carbon-14 production.
Yeah, so carbon-14 first. Well, carbon-14 start has been delayed by a little bit. We're hoping to get carbon-14 out, over the summer. So the carbon-14, the feedstock shipping process for carbon-14 is quite complex. The feedstock is actually processed in, the raw material comes from Canada as nuclear waste. It gets shipped to Tennessee, where it gets converted into carbon dioxide gas that can be shipped to ourselves. The gas then gets shipped from Tennessee back to Canada, and then the Canadians ship it to us, and then we start processing it. There's been a delay at the Tennessee site to get the carbon dioxide out from there. So we're likely receiving our feedstock in the next sort of 2 weeks or so, 3 weeks, and then we'll be able to start processing it, start having first deliveries in the kind of November timeframe. That's carbon-14. Second question was relating to Iceland. So we have 3 out of the 4 permits we require to start building in Iceland. We have an energy agreement, which is a very attractive, sub 5 cents per kilowatt hour, fixed for over 10 years. We found some real estate. We've negotiated an MOU for a lease. We are in the final stages of putting together the first contract. It'll be serviced from Iceland. And so, when all that comes together, which will hopefully be over the summer, then we can start building our first plant. We're hoping that Iceland will start producing during August of 2025. That's when the customer needs it. And so we're working hard towards that date, which means we have to start building this plant in the August-September timeframe this year.
And thank you for that. Amaya asks, is your revenue going to be based solely on enrichment, or are you going to be selling any hardware or licensing any technology?
Oh, good question. So I think our revenues initially will be from a number of areas. So first of all, it'll be sale of isotopes, both radioisotopes in PET labs and stable isotopes in ASPI. And then, right now we're doing some service work for a large SMR company. So a large SMR company is paying us $2 million to do a piece of research work for them into nuclear fuels and nuclear fuel best practices and designing a plant, that kind of thing. And then, if we spin out Quantum Leap, in theory, ASPI has a EPC contract with Quantum Leap. And so all the construction, the procurement, the engineering, the design, that will all be, all the costs of that will end up as revenue for ASPI. So there'll be a mixture of revenue lines, hopefully in 2-3 years' time.
Fantastic. And Art asks if there are any end products that are harder and more fragile to handle than the others, and if so, how are you handling them?
Yeah, so I mean, no product is easy to handle. Let's say that. We typically deal with very nasty gases. So carbon dioxide, we get the carbon dioxide from our Canadian customer. We convert it to methane because we'd rather enrich methane, and that's radioactive. So, it's only a beta particle, so it's not particularly radioactive, but it is radioactive. So it requires all of the hazardous safety protocols you'd put in place for processing a radioactive gas. When we process silane, silane is pyrophoric. So if it touches oxygen, it explodes. So simple answer, keep oxygen out of the plants. But sometimes that's easier said than done. There has been the occasional bang from our research facility. And the same is true for dimethyl zinc, which we use for zinc. That's also pyrophoric. Something like molybdenum hexafluoride is reacts with water very aggressively to produce hydrogen fluoride, HF, and that is extremely toxic, extremely poisonous. So, most of the materials we handle are not particularly friendly materials. We have 70 employees, 20% of them have got PhDs, 50% have got advanced degrees, mainly in things such as chemistry, chemical engineering, that kind of stuff. We actually have 2 PhDs, chemical engineers who specialize in fluorination chemistry, which is the most toxic chemistry you can imagine. So we have a lot of dangerous materials, but we know how to handle them. And our scientists, that's their job, is to handle them, make them safe.
So the short answer is yes. All right. We have a little bit more time. I want to ask a few more questions. Lots of questions for you today, Paul. Dean asks, are there funds you can grab to build a plant in the U.S.? It seems like the government is battling foreign chip and semiconductor manufacturing, and it only makes sense that there would be grants available to keep this process in-house. What are your thoughts?
Absolutely, yes. So we would love to come to the United States, and the United States needs this technology. It's the country that needs it most out of anywhere. Getting environmental permits in the United States is often harder than getting them in other countries. In the United States, you'll find you put your environmental permit in, and locals will find that there is a rare bird that breeds at your site every 10 years, and you're not allowed to build your facility there. Whereas in South Africa and places like that, you'll find the bird just moves to a different field and it breeds there instead. So, different types of hurdles, but absolutely our goal is to come to the US. We just have to recognize the permitting process, the regulatory process, the licensing process is a slower, longer process than it is in other countries. And we've selected countries where we think we have a clear, short, fast path to market, because the world needs these isotopes today. It needs them right now, and we can't be waiting for a permit while the world is waiting for our isotopes.
Perfect. And Howard asks if you have a specific target date to begin commercial production and what needs to be done to meet that target.
Yes, I mean, for carbon-14, the plant's operating right now. It's working. It's enriching carbon-13. We just need our feedstock from Canada, so we're waiting for that, and that will allow us to go into commercial production during the second half of the year. For silicon-28, we have the feedstocks actually in South Africa now. We're just waiting to finish off the plant. That'll be finished off momentarily, and we'll probably start commissioning that and producing there. So, we're hoping to start, and then ytterbium will start enriching that hopefully in September of this year. Ytterbium, we had said 2025. We've brought that forward to about 9 months just recently. It's very rare schedules move to the left. They normally move to the right. But in this case, we found a lot of the permits we needed. We obtained a lot quicker than we expected. We required export and import permits from multiple countries. A lot of bureaucracy, but we got them very quickly. And that plant is in the final stages of being built now. So bottom line is, 3 plants hopefully being commissioned between now and the end of the year to start commercial production.
You've touched on this, but Brett asks, when might you be cash flow positive, and when will you deliver against your carbon-14 contract, and any further anticipated capital raises? The most recent one surprised him.
Yeah, so in terms of cash flow positive, we'd like to think that we can exit this year with PET Labs and ASP Isotopes both being cash flow positive. Obviously, Quantum Leap Energy is still some way off. And so I can't really give any guidance there. It depends a lot upon government permits and what have you. Capital raise surprised you slightly. Yeah, so we were going to do an IPO instead at Quantum Leap, and we decided actually we're better off doing a capital raise at ASPI and dropping that cash down. So there's always going to be some dilution coming in an IPO at Quantum Leap. That's probably not going to happen anymore. We've just done it now. There's a third part for that question. I've forgotten what it is.
It was more any further anticipated capital raises.
Yeah, so the goal is no. The goal is not to have anymore.
Okay, great. Well, Paul, you have more questions, but we're kind of out of time. So any closing remarks for our viewers?
Listen, thanks for your interest. Thanks for your support. It's an important time for this industry in the world. We need more of these chemicals, and we look forward to trying to help bring these new chemicals to the world to make new technologies that everyone can enjoy. Thank you for your interest.
Perfect. Thanks for joining us on the conference again, and we'll see you again in the future.
Thank you.
All right, everyone, stay with us. We'll be right back with SIOS.